Hi everyone and welcome back to NTE. So I was asked recently to do a question on titration, right? So specifically to focus on acid-base titrations, right? So this is basically what we're doing today. Okay. Right, so I decided to use question 7 from November 2015 because it is one of the trickiest acid-base titration questions that I could find, okay, well, in the given space of time that I had, okay. Right, so we'll go through the whole question, but basically the acid-base titration part is over here in question 7.2. Right, so we'll get to that. Okay. So when we read this, right, it says that ammonium chloride crystals, right, and we're given the chemical formula for that, dissolves in water to form ammonia and chloride ions, okay? The ammonium ions, right, further react with the water according to the balanced equation provided below, right? Right, so if you look at the equation that has been provided to you, you can see this is also a acid-base reaction, okay, where your ammonium, right, ion over here is acting as the acid, okay, and remember that that is a data covalent bond, right? If I just quickly remind you of that. Right, so with a plus charge like that. Okay, so that hydrogen is actually bonded to the lone pairs of the nitrogen, right? So we call that a data covalent bond, right? So that hydrogen can freely leave, right? Ammonia is more than willing to give up that hydrogen, right? So then the ammonium plus ions, right, basically act as the acid, right? The liquid water which is surrounding it, okay, accepts that proton, okay, and become a hydronium ion, right? So in other words, water over here is acting as a base, okay, right? So that is using the Bronsted-Lowry, right, definition of an acid and base. Okay, but that's not really important. Just wanted to remind you. Okay, 7.1.1, it says write down the name of the process that is described by the underlined sentence. Okay, so the underlined sentence says the ammonium ions react with water. Okay, right, so when you basically are looking at this, right, we know that the ammonium ions came from the ammonium chloride crystals, right? So that sentence is talking about the hydrolysis of a salt, okay, because that salt is basically reacted with water, okay, so that's just straight from theory, okay. So we call this process that's happening here a salt hydrolysis. Okay, 7.1.2, okay, it now asks, is ammonium chloride acidic or basic in aqueous solution? Give a reason for your answer. All right. So now remember that whenever you're asked if a salt is acidic or basic, right? So basically the solution in which that salt is found, okay? Also something else that you should know is that all salts, okay, are ionic compounds, okay? So they are just going to completely dissociate when they are dissolved in water, okay? So basically, whenever you're asked, is a salt acidic or basic, then you just need to work backwards and try to figure out where did that salt come from, okay? Okay, so if you work backwards, right, then you can see that this could have been produced by the base ammonia, right, plus the acid hydrochloric acid. Right, so if we classify these two components, right, we know that the ammonia is going to be a weak base, okay, and the hydrochloric acid is a strong acid. We all know this. So now you can see that where this salt comes from, right? It comes from a strong acid and a weak base, right? So the strong part will always be dominant on the other side as well, right? So then basically this salt is a acidic salt, right? So the solution that contains the salt will actually be acidic. Okay. Right, so we can even put AQ over here, right, because we're talking about these things being dissolved in water. Okay, let me just give you another example of this, just so that you can get a hang of it, right? So imagine if they gave you, or they wanted to know, is the salt sodium sulfate? Okay, they're asking you exactly the same question. Is the salt acidic or basic, right? Then you basically work backwards, right? And you say to yourself, okay, sodium, what do I know that in terms of an acid or a base that contains sodium? Well, it's sodium hydroxide, right? And that, right, reacting with what contains a sulfate, anion, in terms of an acid or a base, that has to be sulfuric acid. Okay, obviously an AQ there as well, but I'm going to leave it up for now. Right, now the difference here is that this specific base, right, has a hydroxide anion there. So actually with this one, it will be that complete reaction of an acid plus a base creates a salt plus water. Okay, right, and I'm going to leave this for you to verify, right? In other words, verify it by checking that everything is balanced, right? I can already see I need to balance my sodiums over here. Okay, but basically the balancing is not what we are concerned about. We want to answer this question: is sodium sulfate, right, a acidic or basic salt, right? So then you check the strengths of your acid and your base, right? So we see, okay, sodium hydroxide in this case is a strong base, right? And then sulfuric acid is also a strong acid. Okay, so now because you have a strong acid and a strong base, right, it means that this salt is actually a neutral salt. Okay, because when these two react completely, right, the pH of the solution ends up being exactly 7. Okay, so then we call this a neutral salt, right? So that means that if you dissolve sodium sulfate in water, right, that solution is going to be a neutral solution. Okay, and that is in contrast to that, sorry, is that if you dissolve these ammonium chloride crystals in water, right, that solution that you make is actually going to be a acidic solution. Okay, so let's just take one more example just to hammer this through, right? Let's say they were looking at the salt sodium acetate. Okay, so sodium acetate like that, right? Work backwards, right? This is your salt. Okay, you know that it came from a acid and a base, right? You just need to identify which acid and base it was. Okay, so when we look at this, right, again we see sodium, so that must have come from sodium hydroxide. Okay, and then when we look at the other ion, right, which is this acetate minus ion, okay, that came from acetic acid, right, which is one of the acids that you're required to know. Okay, this comes from organic chemistry. Okay, again you have that hydroxide there in your base, right, so this is going to be a complete reaction where you have a base plus an acid forming a salt and water. Okay, just quickly check the balancing, looks good. Okay, all right, so now once we've done that, okay, so now once you've basically identified which acid and base formed this particular salt, right, you then classify the acid and base in terms of, is it a strong acid or is it a weak acid, or is it a strong base or a weak base. Okay, so now for sodium hydroxide, we already know that is a strong base. Okay, now acetic acid, you must know this, right? This is a weak acid. Okay, an acetic acid is basically vinegar, right? If you didn't know. Okay, right. So now let's compare, right? So we have a strong base and a weak acid, right? So again, like I said, the strong people always win, right? So then this salt, right, is going to be a basic salt. Okay, so this is going to be a basic salt, right? So if we think about pHs, right, the pH over here is going to be greater than 7, right? The pH of this solution is going to be equal to 7, and the pH of that original solution is going to be less than 7. Okay, now we don't consider the case where you're looking at a weak acid and a weak base. Okay, so this question also said we need to give a reason for our answer as to why the solution of ammonium chloride, right, will be acidic or basic, right? We said that it's going to be acidic, and the reason is going to be because it's produced by the reaction of a weak base, right, ammonia, and a strong acid, hydrochloric acid. Okay, so then you can even add over here, therefore, the pH of the resulting solution will be less than 7. Okay. Right, so let's get to this question 7.2. Okay, and I want you to focus very well in this question. Okay. Now, we are told that a certain fertilizer contains 92% of ammonium chloride. Okay. Now, just notice the fact that they are just carrying down, right, the compound. Okay. This question has nothing to do with any of the equations that were provided to you in the previous question. Right? This is its own question by itself, right? They're just using the same compound, ammonium chloride. Okay. Now, a sample of mass X grams, right, of this fertilizer is dissolved in 100 centimeters cubed of a 0.1 mole per decimeter cubed solution of sodium hydroxide. Okay. Now, the sodium hydroxide is in excess, right? That's very important. Okay. So whenever they tell you that something is in excess, right, then you know that whatever reaction is going to be carried out, right, that reaction is going to go to completion. Okay, and once that reaction is complete, okay, that substance that they told you is in excess is going to be left over. Okay, now here's the reaction that occurs, right? So they tell us that in that fertilizer you have some ammonium chloride, right, which we already know has this formula. Okay, that reacts with the sodium hydroxide, okay, because they dissolve this fertilizer in a solution of sodium hydroxide. Okay, and this forms some ammonia gas. Right, so plus water. Okay, now the important thing as well is that they already tell us that this equation is balanced. Okay, now there is two sections to this question, right? So I'm going to read the entire question so that we get sort of like an overall idea of what's going on. Okay, we know that the first thing they do is they take this fertilizer, which contains some ammonium chloride, and they dissolve it in a solution of sodium hydroxide, right? That first step that they do, okay, the sodium hydroxide is in excess, okay? So the first reaction that occurs goes to completion, okay? So which means that all of the ammonium chloride, okay, crystals that were actually added to the sodium hydroxide, they react completely, okay? All right, so next what they do is that during a titration, right, 25 centimeters cubed of the excess sodium hydroxide solution is titrated with a 0.11 mole per decimeter cubed hydrochloric acid solution, okay? At the end point, it is found that 14.55 centimeters cubed of hydrochloric acid was used to neutralize the sodium hydroxide solution according to the following balanced equation. Okay, now let's now conceptualize what happened. Okay, so we said that, okay, we have some X grams, right, of fertilizer, right? We take these X grams of fertilizer and we dissolve them, right? I'm going to use a beaker, right? We dissolve them in a certain solution of sodium hydroxide, okay? So this is sodium hydroxide. Then what happened inside of this little beaker is this reaction up on top, okay? So basically after that, right, the reaction occurs, right, and then in this beaker we end up being left with the excess, right, sodium hydroxide, right? So now here we've got excess sodium hydroxide. Basically in here, right, you have a certain number of moles, right, of sodium hydroxide that are in excess, okay? So we still have some number of moles, okay, of sodium hydroxide that are in here, okay, and that's the number of moles of sodium hydroxide that are in excess, okay? Notice that the volume won't change, okay? It's still going to be 100 centimeters cubed, okay? All right, so now from there what they did is that they took only 25 milliliters of this excess solution, okay? So now we're going into the titration, right? So I'm going to try my best to represent this, right? So in this conical flask, right, we have 25 centimeters cubed, right, of this excess sodium hydroxide. So we put that in here. Okay, so that's the 25 centimeters cubed, right, of the excess sodium hydroxide. Okay, so basically from this beaker, right, we take only 25 centimeters cubed and we pour it into a conical flask. Okay, so now this is then attached okay, to a burette. Not really trying to make this pretty, but yeah. Okay, so we put a burette over there, okay, and in this burette, what we fill the burette with is some hydrochloric acid. Okay, so let's just see from the information. Okay, this hydrochloric acid has a concentration of 0.11 moles per decimeter cubed. Okay, and it has a volume, right, or actually it has some volume, but basically the volume that we added, right, to the sodium hydroxide that's in the conical flask, right, so that the reaction goes to completion, right? So in other words, when they use this word neutralize, okay, then we know that that's also another way for them to tell us that the reaction had gone to completion, right? Then basically we're just going to write here that 14.55 centimeters cubed, right, of HCl were added, okay, into this conical flask, right, to completely neutralize the number of moles of sodium hydroxide that are currently in that conical flask. Okay, so for our volumes, right, we know that we have to be working with the volumes in decimeters cubed, right? So you can do that in your calculator, but what I'm going to do is I'm going to quickly just convert all of these volumes, right, to decimeters cubed. So question 7.2.1, okay, is asking us to calculate the number of moles of sodium hydroxide in which the sample was dissolved. Okay, what sample are they talking about? They're talking about the sample of fertilizer. Okay, so basically what they're asking us to calculate is the original number of moles, okay, of sodium hydroxide that we had in this beaker before we added the sample of fertilizer. That's going to be easy because we can use the formula concentration is equals to number of moles divided by volume. Okay, so we have that the concentration of sodium hydroxide was originally 0.10 moles per decimeter cubed. Okay, we're looking for that N, and the volume is 0.1 decimeters cubed. Okay, so then if you work this out, right, you get that the number of moles, right, of sodium hydroxide that we originally had works out to be 0.01 moles. Okay, and you just write this for clarity of sodium hydroxide. Okay, so I'm going to take this back to our sketch over here, right? So I'm going to say number of moles of sodium hydroxide is equal to 0.01 mole. Right, so now moving on to question 7.2.2. Okay. Now it's asking us to calculate the mass, right, X in grams of the fertilizer sample that was used. Okay, so now notice what we are asked to calculate. We are asked to calculate this original mass of fertilizer that we added to the sodium hydroxide. Okay, so we're going to have to work backwards. Okay, so let's start over here, right, with the step of the titration. Okay, now we know that the titration goes to completion because we have this word over here, neutralize. Okay, so neutralize basically means that the number of moles of, in this case, acid, right, that were added to the number of moles of your base, right, those were exactly equal. Okay, so whenever a acid or a base neutralize each other, equal number of moles react. Okay, right, so that means that now we then need to be concerned, right, because they told how much volume was needed for that neutralization to occur, right, we then need to be concerned by how much, right, moles of hydrochloric acid was actually added. Okay, so once we know the number of moles of hydrochloric acid that was added to this conical flask, we immediately know the number of moles of sodium hydroxide that were actually present in that conical flask. Okay, and we can say that, right, because of this 1-to-1 stoichiometric ratio, right, between the hydrochloric acid and the sodium hydroxide in the balanced chemical formula that has been provided to us. Right, so now we can add to the sketch that in this volume, right, you have 1.6005 times 10 to the minus 3 moles of sodium hydroxide. Right, so now our next step is to do sort of like a scale factors type of situation, right? Because if you think about it, what happened when you were going from taking this beaker that contained the excess sodium hydroxide and you poured only 25 centimeters cubed of that solution into a conical flask, right, is that you were transferring. Okay, so we need to work backwards using a scale factor, right, to find out these unknown number of moles, right, that were originally in excess, right. So we can easily do that, right. So we just calculated now that we have 1.6005 times 10 to the minus 3 moles of sodium hydroxide in, you can use the decimeters cubed or the centimeters cubed, it won't really matter. I'm going to use the centimeters cubed, right? So this number of moles is in 25, right, centimeters cubed. Okay. Now I want to know how many moles, right, of sodium hydroxide were originally in excess, right, in this beaker before I did my transfer. Okay. And we know that in that beaker we had a volume of 100 centimeters cubed. Okay. So now we check. Okay. We check to see that, well, to go from 25 to 100, we need to times by 4. Okay, so that's the scale factor. Okay, so it means that in order for us to find out what is this x, we need to times this number of moles by 4 as well. Okay, right, so if you work that out in the calculator, you'll get that therefore x, right, is equal to 6.402 times 10 to the minus 3 moles of excess, right, sodium hydroxide. Okay, so I'm going to fill that in our diagram here. These number of moles in the excess beaker that we didn't know, we now know is 6.402 times 10 to the minus 3 moles. Right. So now continuing on with this whole working backwards situation of us, right, we now just calculated the excess number of moles of sodium hydroxide. Okay, this is now going to allow us to calculate the number of moles of sodium hydroxide that reacted. Okay, so that is going to be helpful because then going back into this original, right, equation that we wrote here at the top, right, we know that the ammonium chloride crystals were basically the limiting reagent, right? So then the number of moles of sodium hydroxide that completely reacted is going to be equal to the number of moles of ammonium chloride crystals that were added into the original beaker, right, this beaker number 1 over here. Okay. Okay, so I'm going to put that amount right here at the top. Okay, so 3.598 times 10 to the minus 3 moles. Okay, I'm just going to write here reacted. Right. Okay, so now just to pull things together, right, remember that when we calculated the number of moles, right, going back here to this titration step, right, remember that when we calculated the number of moles of hydrochloric acid that were added, right, we then went to this balanced chemical formula over here, right, to then calculate the number of moles of sodium hydroxide that were present in the conical flask. Okay, and luckily for us it was a 1-to-1 ratio, right? So then it means that the number of moles that were added is equal to the number of moles that were present if the reaction goes to completion. Okay, now we're going to use a similar piece of reasoning. Okay, we just calculated the number of moles of sodium hydroxide that reacted, okay, in this first formula. Okay, so now using the same logic of the stoichiometric ratios, we can now say that because there is a 1-to-1 ratio between the ammonium chloride crystals and the sodium hydroxide, right, then we can say that therefore, right, 3.598 times 10 to the minus 3 moles of ammonium chloride were present in the sample. Okay, so were present in the sample. Okay, I'm going to put this amount back over here, right? So 3.598 times 10 to the minus 3 moles reacted as well. Okay, so we are almost done with the solution. We just need to now go to a periodic table and convert these number of moles, right, of ammonium chloride crystals that reacted into grams. Okay, so we need the molar mass, right? I just want to change my color over here. Right, so we need the molar mass, right, of the ammonium chloride. Okay, so from the periodic table we get 14 grams per mole for nitrogen plus 4 times 1 gram per mole for the hydrogen. Okay, and then we're going to have plus for the chlorine we have 35.5 grams per mole. Right, so this gives us a molar mass of 53.5 grams per mole. Right, so then therefore, right, we can then say, right, that the mass of ammonium chloride, that is going to be equals to the number of moles okay, times the molar mass. Right, and if you work that out and you write it to 2 decimal places, that gives you 0.19 grams. Okay, right, so we are going to say that this is equivalent to 0.19 grams. Right, so those number of moles is equivalent to 0.19 grams of ammonium chloride. Right, now we have finally reached our final step. Okay, right, so because we were not asked to calculate the mass, right, of ammonium chloride crystals, right, that were within the fertilizer, we actually asked to calculate the mass of the fertilizer itself. Okay, now we need to add a final step. Okay, we're going to say, therefore, if you think about how this was calculated, if you take the mass of ammonium chloride, right, which is in the sample, and you divide it by the mass of the fertilizer or the sample, okay, and you times that by 100. That is what gave them that 92%. Okay, because basically that 92% is saying the percentage of ammonium chloride right in the sample. Okay, so if you then fill in the values here, we have 0.19 grams there, right, divided by an X amount of grams for the sample. Okay, and that's times by 100 is equals to 92%. Okay, so then therefore X is going to work out to be, if you write it to 2 decimal places, right, it's going to be 0.21 grams. Okay, right, so just to summarize so that everyone is on the same page, right, the word excess, right, is sort of like a tip to tell you that the reaction is going to go to completion. Okay, so whenever you have something in excess, you need to be aware that that specific thing, right, is going to be left over, right. So then you're going to have to find out how much of it actually reacts and how much of it stays behind. Okay, also in the titrations, right, the word neutralize is used to tell you that the reaction has gone to completion. Okay, so when we say that an acid or a base neutralize each other, right, it means that equal number of moles, right, in terms of the stoichiometric ratios, of course, equal number of moles, right, of that acid and base react. Okay. Okay, so for the final question, question 7.3, right, it's asking you to calculate the pH of a 0.5 mole per decimeter cube sodium hydroxide solution at 25 degrees Celsius. Okay, right, so now this is a base, right? So sodium hydroxide is a base, right? So for me, the way I think about this is that a base doesn't have a pH. A base has a pOH. Okay, so I can easily calculate the pOH using a similar formula to pH, right? So it's going to be the negative log of the hydroxide concentration. Okay, all right, so now sodium hydroxide, okay, is a strong base. Okay, so if you take sodium hydroxide and you pour it in water, okay, it's just going to form sodium plus ions in solution and hydroxide ions, okay, completely, right? So it's a single error. Okay, so now you can see that there's a 1-to-1 stoichiometric ratio again between the sodium hydroxide and the hydroxide ions. Okay, so if we are talking about a 0.5 mole per decimeter cubed concentration of sodium hydroxide, it means that there is also 0.5 mole per decimeter cubed concentration of hydroxide ions. Okay, so we can just put that in there, 0.5. Okay, so if you work this out in the calculator, it's 0.301029997. Okay, the reason why I'm keeping all of those decimal numbers is because I'm not done. I'm not asked to calculate the pOH, I'm asked to calculate the pH, right? So this is now going to go into the formula pH plus pOH is equals to 14. Okay, so then therefore the pH in our case is going to be 14 minus 0.301029957. Okay, so this works out to be 13.69897. Okay, so then therefore the pH, okay, is equals to, we round this off to 2 decimal places, we're going to have 13.70. Right, so then that brings us to the end of today's video, matriculants. I hope you learned something, and I will see you guys next time.